In section 3, we're going to take a look at sampling distributions for a difference in sample proportions. So if you're comparing two proportions or means based on random sampling or a randomized experiment, it's a very common situation encountered in statistical practice. So the goal is to determine whether or not two treatments cause the observed difference, and then to draw a conclusion about the population for all subjects. So we're going to take a look at this through an example. So we want to know which of the two popular drugs, Lipitor or Pravachol, helps lower bad cholesterol more. So researchers used 4,000 people with heart disease as subjects, and they were randomly assigned to one of two treatment groups, Lipitor or Pravachol. At the end of the study, researchers compared the proportion of subjects in each group who had died, had a heart attack, or suffered other serious consequences within 2 years. So let's go ahead and start by drawing a randomized design for the experiment. So we start off with our 4,000 subjects, which are going to get randomly assigned to our two drugs. So that means 2,000 were assigned Lipitor and 2,000 were assigned the Pravachol. And then we're going to compare results. So at the end of the study, for those who used Pravachol, the proportion who died, had a heart attack, or suffered serious consequences within the 2 years was 0.263, and for Lipitor, it was 0.224. So what we want to know is, could such a difference have occurred purely by the chance involved in the random experiment? So what we're basically trying to figure out is, could this be due to chance variability, or an actual difference in the drugs? So that's what our aim is when we're doing a difference in proportions. So a couple things when it comes to notation. So you're going to have your two populations or your two treatment groups. All right. They're each going to have their own parameter, P1 and P2. They're each going to have their own statistic, P1 hat and P2 hat, and they're each going to have their own sample size, N1 and N2. Now, N1 and N2, our sample sizes, could be the same. They could be different. They should be close to one another, especially if you're wanting to make a comparison. You don't want your sample sizes to be too different in size, because then we can't really tell if it was due to chance variability or an actual difference. When it comes to the sampling distribution for P1 hat minus P2 hat, so again, we're looking at this difference in our sampling distribution. The three conditions still have to be met when it comes to if we were looking at a single proportion. So the shape should be approximately normal, just like it was for a single proportion. Now, when it comes to when you check that condition, not only do you have to check it for the first proportion, so you have to check that N1 P1 is greater than or equal to 10, and N1 times 1 minus P1 is greater than or equal to 10. You have to check it for the second group as well. So N2 P2 has to be greater than or equal to 10, and N2 times 1 minus P2 has to be greater than or equal to 10. So you have to check that both distributions are normal, and then we can say that their difference is normal. When it comes to calculating our mean, so mu sub P1 hat minus P2 hat, it's as straightforward as just subtracting them. So you take the mean of your first distribution and subtract the mean of your second distribution. Very similar to when we were doing the combining for distributions. And then for the condition, you have to have that both are randomly designed if you're looking at an experiment, or it's an SRS, or there's a random choice. And lastly, our spread, our standard deviation. So now this is going to be different from when we were looking at the combined distribution. So it's not as simple as that formula. So what we actually have to do is underneath the square root, we have to do P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. Basically take the standard deviation formula for one proportion and we combine it, and we have to do it for each. And then for our condition, we still have to make sure the 10% condition is met for both samples. So N1 has to be less than or equal to 10% of its population, and N2 has to be less than or equal to 10% of its population. So you have to check normal and spread, normal and independence twice. Random, you really only have to check once. So let's go ahead and take a look at an example. So suppose you have two large bins of several thousand plastic beads. Bin A is 60% red beads and bin B is 48% red beads. Suppose you take a random sample of 80 beads from each bin and calculate your proportion of red beads from bin A, and your proportion of red beads from bin B. So we want to describe the sampling distribution for the difference in proportions between our two bins. So when it says describe the sampling distribution, we want to check that it's random, independent, and normal. So we want to check that our shape, our center, and our spread. So for random, it does state that you are taking a random sample So that tells me that the mean of PA minus P hat B is going to be, I can just subtract the proportions, so 0.6 minus 0.48, which is going to give us 0.12. Next, we're going to check independent. So we have to make sure that our sample size, and because our sample size is the same for both of these, and they're from the same population size, I don't really have to check both of them. So 80 has to be less than or equal to 10%, and we know we have several thousand beads. So we know our distribution is also independent because both bins are the same size and we're taking the same sample from both. So I really don't need to check it twice. So that tells me that the standard deviation for my distribution, I'm going to do the square root of 0.6 times 0.4 over 80 plus 0.48 times 0.52 over 80, which is going to give us a standard deviation of 0.0782. And the last thing I have to check is that the distribution is normal. Now this one I do have to check for both distributions because the proportions are not the same. So I have to make sure that 80 times 0.6 is greater than or equal to 10, and 80 times 0.4 is greater than or equal to 10. And considering 50% of 80 is 40, I definitely, 60% is greater than or equal to 10. It also tells me 40% is also greater than or equal to 10. And then I have to check that 80 times 0.48 is greater than or equal to 10, and 80 times 0.52 is greater than or equal to 10. And again, because both of these are fairly close to 50%, and 50% of 80 is 40, our distribution is also normal. So we have all three of our conditions. We know our mean and standard deviation. So we want to find the probability that the proportion of red beads you select from bin A is higher than the proportion of red beads you select from bin A. So now we're going to write our probability statement. So because our distribution is defined as p hat A minus p hat B, that's how I have to write it in my parentheses. So if we want bin B's proportion to be higher than bin A's, their difference is going to be negative. So we're looking to see if the probability their proportion is less than, their difference is less than 0. So because I've already checked all of my conditions, I can go ahead and go to normal CDF. So my lower bound is going to be negative 1E99. Upper bound is going to be 0. My mean is 0.12, and the standard deviation is 0.0782. So you go to second vars, you plug in your information, and we're going to get a probability of 0.0625. And then my last step is to write a sentence. So the probability, the proportion of red beads from bin B is greater than the proportion of red beads from bin A is 0.0625. So it's not very likely that the proportion of red beads from bin B is greater than the proportion of red beads from bin A. So let me know if you have any questions about doing a probability question for a sampling distribution for a difference in sample proportions.